What's up everybody, welcome to another video. Hope you're ready to flex those brain muscles. In this video I'm going to teach you about even functions and odd functions, and I'm going to help you thoroughly understand them. The symmetry of their graphs, the formal definition you're going to actually have intuition for. We're going to look at a bunch of examples. I'm going to show you how to prove a function is even, how to prove a function is odd, and actually by the end of this video you're going to be able to tell if a polynomial function is even, odd, or neither by just looking at it. So let's go ahead and thoroughly dive into even functions and odd functions. And we're going to start by looking at an even function from a graphical perspective. So a function is even if its graph is symmetric about the y-axis. So here's an example, f of x equals x squared. This is an even function, should be a function we're all familiar with. And if I draw this vertical line down here, right, the line x equals 0, or the y-axis, then hopefully we see this symmetry. If I fold this function over, it lands on itself. It's like a reflection or a mirror, different ways to think about it. Hopefully we see this symmetry, and the same thing happens with this function, f of x equals x to the 4th power. We see that same symmetry. And finally, here's a fun one, f of x equals the cosine of x. So even if you're not familiar at all with cosine or its graph, hopefully you can look at this graph and tell that we have this symmetry. We can draw this vertical line and we can fold the right side over and it lands on the left. So let's use this symmetry to help us understand the formal definition of what it means for a function to be even. So a function is even if f of x equals f of negative x for all x in its domain. So this is, again, function notation. Inside the parentheses here we have inputs or x values. What's the relationship between these two inputs or x values? They are of opposite sign, right? So if x is 1, for example, then negative x is negative 1. If x is negative 2, for example, then negative x is negative 2, which is just positive 2. So we're taking inputs or x values that have the opposite sign, but this equality, right, this equation isn't relating directly to x values. It's relating to outputs or to y values. It's saying f of x, that's an output. That's the y value when the input is x, is equal to f of negative x. So one way to think about what this statement says is that if we have two inputs or x values of opposite sign, then their outputs are equal. So 1 and negative 1, for example. If x is 1, negative x is negative 1, what is f of 1? That's a y value. So I'm looking when x is 1, what is the y value? That's 1, and we're comparing that to f of negative 1. That's also a y value, which is also 1, and so these two are equal. So again, when we have inputs or x values of opposite sign, then their y values are always equal. We can do the same thing here. What is f of negative 2? So that's going to be our x in this case, and that's over here, that's 4, and we're comparing that to f of positive 2, right? Negative 2 is positive 2, which is also 4, and these are equal. Awesome. So we're relating two y values. That's what this definition is saying. That again, if we take two x values of opposite sign, their y values are equal. And we can see the same thing over here. If we look at it from a table perspective, 2 and negative 2 are opposites. Their y values are equal. Negative 1 and 1, opposite x values, their y values are equal. And we could sort of think of this also in terms of distance, is one way I like to think about it. If we go some distance to the right, and that's our x value, then the y value that corresponds to that x value is the same as if I go that same distance to the left and find that y value. So it really aligns perfectly with how we think about this symmetry about the y-axis. So hopefully this definition is making some sense. Let's go ahead and see if we can use it to prove that this function is even. So what do I want to show? I'll make a note here, want to show that f of x equals f of negative x. And how we typically show that is if we're given a function f of x in this form, then we just figure out, well, what is f of negative x equal, right? Sorry, f of negative x. And we want to write this out and do some simplifying, and hopefully what we get to is that this is equal to exactly this function which we're given, which is the definition of even. So that's what we're going to try to do here. I'm going to plug negative x in for x. So f of negative x is 3 times negative x to the 4th power minus negative x to the 2nd power, and then plus 1. All right, so this is a little bit tricky, but once you kind of see the idea, you should get the hang of it pretty quickly. The 3 can just chill out in front. And what is negative x to the 4th power? That is negative x times negative x times negative x times negative x. together we have 4 x's multiplied together, and we have 4 negative signs that are all going to cancel out, and the result is going to be positive. And if you don't see that, let me go ahead and write it out down here. So this is one way to think about it. I grouped the first 2 negative x's together and the last 2 negative x's together. I know that negative times a negative is a positive, and x times x is x squared, and that happens for each of these pairs. And now all together, I have 4 of these x's multiplied together, and so that's just x to the fourth. So negative x to the fourth is the same as x to the fourth. And hopefully you're kind of seeing how this is going to go, which is that negative x squared is the same as x squared. And we actually showed that here by multiplying negative x times negative x and saying that's the same as x squared. And this is a pretty common thing that's going to happen, especially with polynomials, when you're trying to prove a function is even, or where you have an even function, which is you're going to end up with negative x raised to some even power, and we're always going to be able to say that's the same as just positive x raised to that same even power. So this is making sense, and hopefully you're connecting this with our definition here of even, which is we're plugging in negative x and we're getting the same thing that we would get if we plugged in positive x. And that's exactly what happened here. This is f of x. So our proof is done. We've shown that f of negative x equals f of x, and therefore this function is even. So now let's talk about odd functions, and we're going to do the same thing. We're going to start from this graphical perspective to understand this type of symmetry, then we're going to move toward a more formal definition as well as a proof. So an odd function has a symmetry that's harder to visualize than an even function. It's called rotational symmetry about the origin. So let's talk about this. The origin is this point here, 0, 0. And rotational symmetry means we're kind of thinking about this like a top. That's why I have this picture here. So imagine if this top here, the point, were on the origin, what would happen if I spun this top? That's what I want to think about doing to this function. I want to spin this function. I want to rotate it exactly 180 degrees. That's what we mean by rotational symmetry about the origin. So when I rotate this function 180 degrees, this point 1, 1 moves over here to this point negative 1, negative 1, right? So we're rotating it. This point here, whatever it is, where the y value is 2, moves over here. And in general, this entire curve, we can imagine it spinning, okay? I didn't draw it very well, but we can imagine this entire curve spinning and landing on the other side here on this curve. And additionally, this curve at the bottom spins and lands exactly on the curve on top. So we end up spinning and landing on itself, and that's what we mean by rotational symmetry about the origin. So kind of harder to visualize, but let's look at a couple more examples. And I like this example because it shows that an odd function doesn't have to intersect the origin. It doesn't have to have a point here. It just has to have rotational symmetry about this point. So we're thinking the same thing. I'm taking this point, and when I rotate 180 degrees, what happens? It lands exactly here on this point. And in general, this entire curve, when I rotate or spin this function 180 degrees, lands on this curve, and the same thing happens the other way. This curve lands on that curve. So they sort of swap places here, and we have a function that has this rotational symmetry and is an odd function. And we'll look at one more example here. I really like this example, sine. We see that when we spin this about the origin, again, this point 0, 0, this point lands here. I really like this example because I think it helps visually. This point lands here. Boom. And in general, if I draw this little section here, let me see if I can actually draw it well. This little section here lands right here and vice versa, right? And in general, the entire function is going to land on itself when we spin this 180 degrees about the origin. And that's what it means to be odd graphically. So now let's see if we can relate this to the formal definition, which again uses function notation. So a function is odd if f of negative x equals negative f of x for all x in its domain. So similar to even, we're seeing these inputs as being opposite signs, right? So I'm relating two inputs that are of opposite sign. So if I pick x is equal to 1, then negative x is going to be negative 1, right? If I pick x is equal to negative 2, then negative x is going to be negative negative 2 or positive 2. So different from an even function, I'm not saying that two opposite inputs, right, opposite sign inputs have the same output. We're actually saying that two inputs or x values with the opposite sign, right, negative x and x, have opposite signed outputs. f of negative x equals negative f of x. So that means that if I plug negative 1 into this function, that I should get the opposite of what I get when I plug 1 in. So let's try that out. When I plug in negative 1, I get negative 1. And when I plug in 1, I get positive 1, and the opposite of that is negative 1. So this is true. Okay, we can do the same thing here. When I plug 2 into this function, the output should be the opposite sign of what I get when I plug negative 2 into this function. I think that's the best way to say it in words. So if we take two inputs of opposite signs, their outputs will also be of opposite sign. Okay, so f of 2 equals negative f of negative 2, right? And we can go here on our table and look. We see opposite sign inputs to a negative 2 and opposite sign outputs, negative 8 and 8. Opposite sign inputs, opposite sign outputs, and hopefully we see how this relates to our rotational symmetry. That's what it means to, remember we were going back to these points and we were mapping the point to another point, right? That's what I'm doing here. I'm going the opposite direction this way, and I'm going the opposite direction here, right? So this distance in the x direction, I'm doing that same thing but this direction, and this distance in the y direction, I'm doing that same thing but down. So opposite direction, left, opposite direction, down. Let's relate it to this one. Here, instead of going right by 1 and up by 1, I'm going left by 1 and down by 1. And that's how I'm relating those points to each other, right? Here, similar thing. Instead of going right 1 and up 1, I'm going the opposite x direction and the opposite y direction. So both are opposite is a great way to think of this conceptually. Hopefully that's making some sense. It's a little bit tricky. If you're not fully there, that's okay. Now let's practice showing that this function is an odd function. So this is a little bit more work, because when we're showing a function as even, we just really have to evaluate one thing or find one thing. We're given part of our definition. Where showing odd, we have to consider negative f of x. So let's go back to our definition. F of negative x equals negative f of x. So let's write that out. That's what we want to show, which is that f of negative x equals negative f of x. Boom. Awesome. So that's what we want to show. And so it turns out negative f of x is actually really easy to find here, right? Negative f of x, we're just going to take this and multiply it by negative 1. And some of you may do this in one step. That's totally fine. You can just distribute the negative. You change every sign. And so we end up with x to the third power plus 2x. Awesome. So is this the same thing as f of negative x? That's what we want to show. So what happens when I plug negative x into this function? I get negative x cubed minus 2 times negative x. All right, and here's where we're going to think about what does it mean to raise negative x to the third power. Negative x times negative x times negative x. Two of those negatives cancel, right? But I'm still left with 1. And in general, an odd number of negatives is still going to be negative. So actually, negative x to the third power is negative x to the third power. And I'll make that clear down here. So again, 3 of these negative x's multiplied together. Negative, negative, that makes a positive x squared, but we still have this negative that doesn't go away. And so we just end up with negative x to the third. And in general, this is what's going to happen when we multiply an odd number of negative x's together, which is why our definition here is going to work. Next, we have negative, negative, right? So that makes a positive. And now what we've shown is exactly what we want to, which is that negative f of x is equal to f of negative x, because these two expressions are equal, and therefore we've shown that this is an odd function. And that's going to be a pattern. With odd functions, we're going to be dealing with odd exponents. With even functions, we're going to be dealing with even exponents. And that's kind of what I want to talk about next, which is you can actually determine whether a polynomial function is even, odd, or neither by just looking at it. Remember, these are the two examples we went through. We noticed that our even function had even exponents, and so that's why we were able to say that negative x to the fourth was just equal to x to the fourth. Negative x squared was equal to x squared, right? Where our odd function had odd exponents, 3, and we could think of this as to the first power. So let's hop on Desmos and see if we can sort of solidify and finalize some rules for when we're thinking about polynomial functions. So there's a few key ideas that I want to focus on when it comes to even and odd functions, but I encourage you after you watch this video to open up Desmos on your own and explore, play around with it. You might learn something. So one thing we saw in this video already is that function f of x equals x squared and g of x equals x to the fourth, these are each even functions. I showed you these at the beginning. So the natural question is to notice that 2 and 4 are both even numbers and wonder if x to any even power is always an even function, to the 6th, to the 8th, to the 10th, and the answer is yes. And we already kind of touched on why this is the case, which is that when we have a negative raised to an even power, it's the same as the positive of that raised to the even power. So it's literally just the definition of an even function we can apply and immediately show that x to any even power is even. So then a good follow-up question would be, well, what about adding a constant out in front, like multiplying by 2? Do we still maintain this symmetry about the y-axis? Okay, and the answer is yes to that as well, even when it's an odd number, like 3, even when it's a fraction, like 1/2, and even when it's an irrational number, like pi. Any real number out in front is going to maintain this function being even, and so what we have so far is any function of this form, where out in front we have a real number, and in the exponent we have an even integer, is going to be an even function. Okay, so now I want to think about, well, what about a constant function? And this is a pretty easy one to see. When we have a constant function, it's even. Doesn't matter what the constant is. 2, right? We can do irrational, pi, 1/2, symmetric about the y-axis, any constant function. Okay, and now finally what I want to point out is what we have so far is that functions of this form, number times x to an even power, as well as constant functions, are both even. And so here's a cool thing. This is like the key idea here, is that if we combine even functions with subtraction or addition, then the result is always an even function. So look at this. That first term is even. It's a number, and it's x to an even power. Number, x to an even power. Constant, we said that was even, and the result is something that's symmetric about the y-axis and is therefore even. So this is kind of the key idea, is if we can see a polynomial as being composed of a sum or difference of even parts, then we can conclude that it's even. So let's do a similar thing for odd. So this is one of the odd functions we saw, f of x equals x cubed, and we could do a similar thing that we did to the even functions. Chain this exponent to odd numbers, and what we notice is that for these odd numbers, they all produce odd functions. So f of x equals x to any odd integer power, including 1. This is an odd function. 2, that spins around here to -2, -2. And also 1 over x, remember I showed this example? This can be thought of as x to the -1 power. Let me turn this on. 1 over x is the same as x to the -1 power, so even negative odd numbers are working. I thought that was kind of cool. So we can go back here and we can do the same thing we did with the even functions, which is play around with numbers out in front. Numbers out in front, 2, 3, pi, and these are maintaining the oddness, right, the rotational symmetry that the function has. So any function of the form f of x equals real number times x to an odd power is odd. So now let's look at constant functions. Let's try out a constant function here. And it turns out constant functions are a little weird, right? Rotational symmetry. Boom, this would flip around to -1. So this constant function, g of x equals 1, is not odd. It is even, right, because we have that symmetry about the y-axis, but it's not odd. This point 2, 1 would have to flip around here to -2, -1, right? Again, if we rotate it, we end up with the line y equals -1. So not odd. There's actually only one constant function that is odd. That's g of x equals 0. And in fact, fun fact, this is the only function that is both odd and even. This has rotational symmetry about the origin, and it has symmetry about the y-axis. So that's the only function that's both odd and even. None of these other constant functions are odd. Okay, so using that, let's do the same thing, which is that if we combine a bunch of odd pieces, do we always end up with an odd function? And the answer is yes. But what happens when we add a constant at the end? Remember, that is not odd, it is even. Now it messes with the oddness, right? And this is a really confusing thing. I often show kids graphs like this, and they're like, oh, this is odd because I can rotate it from here, and that lands here, and this lands here. Remember, we're always rotating about the origin. So this point here would actually spin up here, and that doesn't land on a point on the graph. This no longer has rotational symmetry because we've shifted it off the origin. This does, that's odd. -1, that doesn't. -2, that doesn't. So these constants are sort of messing up what we got going on here with the oddness. Finally, what happens if we just straight up add like x to the third, and x squared together, an odd and an even part. And the result is something that's neither odd nor even. So we're going to put all these kind of key ideas together, but hopefully this Desmos exploration helped. So let's summarize what we learned from our Desmos exploration. Functions of this form, a times x to the n, where n is an even integer and a is a real number, are always even. Additionally, constant functions are always even. F of x equals any real number. That's an even function. Finally, a sum or difference of even functions is always even. So if we add or subtract two even functions together, then the result is an even function. We have a kind of similar thing for odd functions, but a little bit different. Functions of this form, f of x equals a times x to the n, where a is a real number and n is an odd integer, are always odd functions. Okay? Additionally, this is the different part. The only odd constant function is f of x equals 0. In fact, this function is the only function that is both odd and even. Okay? So any other constant function, f of x equals 1, negative 5 over 2, pi, whatever it is, that's definitely not going to be odd. It's going to be even. Okay? And finally, a sum or difference of odd functions is always odd. So very similar. If we add even functions together, we get an even function. If we add odd functions together, we get an odd function. Here's a really important key idea, which is a good way to identify that a polynomial is neither even nor odd. If f is an even function and g is an odd function, then if we add or subtract them together, the result is neither even nor odd. And this is as long as neither function is the 0 function. So f of x equals 0 or g of x equals 0. That's a weird counterexample. But if we exclude those, then this is absolutely true. What that means is we can use this to identify whether a polynomial function is even or odd. It's even if it only contains even powers of x, doesn't matter the coefficients that are in front of those powers in those terms, and constants at the end are totally fine. It's odd if it only contains odd powers of x, but remember, constants are not okay. The only constant function that's odd is 0, and we pretty much never write plus 0 at the end of a polynomial. So if it has a plus 1, minus 5, anything like that, not okay. Definitely cannot be odd if that's the case. So what are the primary examples where we see a function that's neither even nor odd? And that's really two things happen. One is that it contains a combination of even powers of x and odd powers of x. Then that would be neither even nor odd. Because for odd, it has to have only odd powers, and for even, it has to have only even powers, right? And so if it contains both, it can't be either. Another common example is that we'll have odd powers of x and we'll have a constant at the end, which again, that's not okay. So that's another example of neither even nor odd. Alright, so we can finish the video with this check for understanding. What I want you to do is determine whether each function is even, odd, or neither by just looking at it and thinking about the stuff we just talked about. What I encourage you to do is go even further, and if you find one that's even or odd, prove it using the formal definition. Practice that skill that we showed earlier in the video. Alright, hopefully you've already gone through this, you paused, you pressed play, you're ready to check your answers. Let's jump right into it. For this first one, I said neither. Because we have this odd power of x here, it can't be even. And because we have this even power of x, it can't be odd. That's one way to think about it. So neither, right? Remember that even functions can't have any odd powers. Odd functions can't have any even powers. What about the second function? Even, constants are okay, right? -1, that's an even function. That's one way to think about it. 1, 2, 3, even functions added or subtracted together. So this one is actually even. And if you proved it, that's awesome, right? You'd end up with -x to the fourth, which is equal to x to the fourth, -x squared. They're all really the same idea. Once you see the pattern, it's all the same. All right, this function, this one's tricky. Very often kids will say odd when I put this on a test, but it's not. Remember that constant is not okay. When we end up comparing -f of x to f of -x, we end up with slightly different things because of that constant that's messing us up, okay? So neither, even though both powers of x are odd, that constant is not okay with odd functions. That was one of our rules. Finally, this is an odd function. Odd power, no constant, odd, and this is going to work out when we actually use our definition to prove it. All right, and that's it. Hopefully this video helped you. Hopefully it made sense. Comment below with any questions. To support me, do all the things. Like the video, subscribe, share it with your friends, with your teachers, all those things. But most importantly, keep flexing those brain muscles, and I'll see y'all later.